Hi everyone, thank you for taking the time to watch my presentation. I hope you find it informative. In this presentation, I'll go over the work I did for the development of a biaxial testing apparatus project over the past summer. In today's agenda, I'll go over the project, some of the reasons why biaxial testing is important in the introduction, followed by a background on biaxial testing and devices. Then I'll go over the setup and design of the biaxial testing apparatus. And finally, I'll go over the results and future work. So this project had two parts to it. Officially in the project charter, one part was called Biaxial Testing Apparatus Development, and the other part was called Hardware-Software Interface for Biaxial Testing Apparatus. My work focuses on the hardware and software interface, which involved programming an Arduino to operate the motors and read the load cell output. So the reason material testing is important is because we need to determine their material behavior under different loading conditions, especially when new material is developed or different ways of creating parts are developed, such as 3D printing. Uniaxial tests such as tensile testing is pretty common for characterizing a material. However, these tests are inadequate for simulating the material behavior in real-life conditions, because most of the time a component is going to experience loading in multiple axes and not just in one direction. For example, aircraft fuselage experiences biaxial loading because it's essentially a pressurized vessel. There are biaxial testing machines available on the market, mostly used in labs and in industrial plants, and these can be a few $100,000. So as I mentioned previously, typically mechanical testing is uniaxial, and you can see the different types of tests that can be done in the figure here. Now, biaxial tests are closer to simulating the conditions that a specific part will be experiencing over its lifetime. And these biaxial tests are often used for fabrics or biomedical materials that are used as implants inside the human body. When we talk about biaxial stress, we mean in-plane stresses that an element experiences across two perpendicular axes. And these stresses can be of the same type, such as tension on both axes, or compression on both axes, or mixed mode, which is, for example, tension along the y-axis and compression along the x-axis. And you can see the different types in this figure here. An example of this, as I mentioned previously, is an aircraft fuselage. One thing to note about this is the curvature effects can be neglected because they're very small if the diameter of the pressure vessel is large enough. Now there's two ways that we can induce biaxial loading on a sample. Here I assume the sample is square shaped. One way is to anchor one side of the sample along each axis and apply the load on the other side. And the other method is to apply load on both sides of the sample along both axes. And the example that you can imagine is like a piece of paper that's being pulled from all sides. In the first method, the center of the sample will move. It's not going to be stationary because it is anchored on one side. So the forces applied will shift the center. But in the second method, the center will stay in place. And this is the preferred method for biaxial testing because it makes it easier for calculating the strain using optical measurements. Biaxial testing machines have actually been around for quite some time. The first one was built in 1913 in Germany, and it was used for testing the fabric that went into constructing zeppelins or airships. You can see an image of the first biaxial testing device on the left side here. Modern biaxial test machines come with a high price tag, especially if a customer needs high accuracy in terms of stress applied and strain measurements, such as the one shown in the image on the right side over here. This particular image is actually from the University of Minnesota. They have this device in their Department of Biomedical Engineering, and it was developed by Instron Sachs. Now, besides the test device itself, the shape of the sample is also very important when it comes to biaxial testing. The purpose is to induce in-plane loads along perpendicular axes, and based on the literature that I've read, the best sample shape is cruciform, which consists of 4 arms that are used to apply loads on the sample, and they have grips so that the device can attach to it properly, and the area of interest or test region in the center. Based on reviewing the literature, I wasn't able to find an exact procedure for creating these samples because most researchers created them using empirical testing of different shapes and sizes for their specific material. But in general, there are 3 criteria that has to be taken into account when creating cruciform samples. The first one is that the central test area must experience homogeneous stress and strain. Second criteria is that the stress on the sample arms has to be compatible to the stress in the test region. What this means is that the sum of the stresses on the arms, which can be calculated by dividing the load by their respective cross-sectional area, has to be similar to the stress experienced by the sample in the test region. And finally, the third criteria is the highest stress level should be observed in the test region, and initial yielding must occur in this area as well. So cruciform samples are the best shape for biaxial testing. However, calculating the stress from applied loads is a lot more complicated than in the case of uniaxial testing. Some other considerations to take into account for cruciform samples is specimen alignment, which is making sure the sample and the test device arms are perfectly level and aligned. The size and uniformity of the applied stress, so making sure the sample arms fit properly inside the machine. Third one is preventing stress concentration outside of the test region, so sample preparation is important. And finally, taking into account stress redistribution after localized yielding. Okay, now moving on to the setup and design of the biaxial testing apparatus. The CAD model you see on the right side was provided by Giovanna Saccaro. She was the other student working on this project. And as you can see, it's pretty straightforward. It must follow the requirements that I mentioned previously, which is applying in-plane tension or compression. And these can be the same on both axes or applied in mixed mode, so different stress types for each axis. Along each axis, there's 2 arms with grips for holding the sample, and these arms are operated by the stepper motor, as you can see in the corners here. And these arms are attached to a 10 centimeter thick steel board, which is important because we don't want any bending or buckling of the baseboard when testing is being done, and this steel board ensures that that doesn't happen. In this slide, we can see how the arms themselves look like. There's a grip that's attached to a load cell, and using a rod, it's connected to a U-support, which has a ball screw at the top. This ball screw translates the rotational motion of the stepper motor into linear motion. And the other component for this motion is the threaded rod that's attached to a stepper motor, as you can see in this figure here. This threaded rod is the one that's passing through the ball screw. The U-support sits on slide rails so that it can move back and forth with ease and prevents wobbling. These slide rails are attached to the baseboard using a machined L bracket. Here we can see the setup of the electronic components of the testing apparatus. So the load cell has to be connected to a load cell amplifier first, because the Arduino cannot read the signals coming from the load cell if it's connected straight to it. The signals need to be amplified first. And the load cell power has to be provided by an external source, because the Arduino can only provide 5 volts, and usually the load cell requires more than that. On the other side, we can see the stepper motor and how they're connected to the Arduino. So each axis has 2 stepper motors, and these need to be run at the same time. So I combine the wires together, and they both are connected to the same digital stepping driver. This digital stepping driver is connected to the Arduino, and how this connection works, basically the Arduino sends signals to the driver. The driver converts the signal to angular displacement signal and sends that to the stepper motors. The power for the stepper motors is also provided by an external source, which goes through the digital stepping driver as well. So stepper motors were selected because of the high precision and position controlling they offer. And also they produce a high amount of torque. They're also flexible for using in both open and closed loop control. They work essentially by energizing a series of coils in sequence, which causes the rotor to start rotating, and that's how the stepper motor operates. And as I mentioned before, the stepper motors are connected to a digital stepping driver, which converts the pulse signals coming from the Arduino to angular displacement signals. To measure the loads being applied to the sample, we used a load cell, which basically works by outputting a change in voltage when the load cell experiences strain. And this change in voltage can be converted into weight or load through the Arduino. And the microcontroller used is an Arduino Uno, which is the most common model of the Arduino platform. It was programmed to take user inputs for load type, so tension or compression, and the strain rate, and send the appropriate signals to the stepper driver to operate the motors. It's also used to read the load cell output and convert to any units that are needed. So the result of my work is 3 programs. The first one is for controlling the stepper motors, where the user inputs through the serial monitor. The serial monitor is essentially an interface for entering data so that the Arduino can read, and also the Arduino data that's being outputted is shown in the serial monitor. So in this program, the user can enter 4 numbers separated by a comma to operate the motors. The first 2 numbers correspond to one axis, and the second 2 numbers correspond to the other axis. Now, from the 2 numbers for each axis, the first number corresponds to the load type, and tension is represented by the number 1, compression by the number 2, and 0 means stop. And followed by the first number, the second number is the strain rate. So an example of this is a user can input 1, 3.4, 2, 3.4. And what this tells the program is I want the first axis to be in tension at a strain rate of 3.4 millimeters per minute. And I want the second axis to be in compression at a strain rate of 3.4 millimeters per second. The maximum strain rate I was able to achieve was 11 millimeters per minute. Now, this program has a couple of issues. The first one is that the strain rate for both axes can't be different. What I mean by this is that whatever strain rate is entered for the first axis is what the Arduino will apply for the second axis. And the second issue is that the motors for the 2 axes don't run perfectly simultaneously. What I mean by this is that one set of motors for one axis runs, and then it switches to the other set of motors for the other axis. Now, these 2 issues, the source of them is the Arduino platform itself, which is sort of limited in terms of capabilities, and it can't run parallel functions at the same time. So what this means is one function has to be executed before the second or any other subsequent function can be executed. So the workaround that I was able to apply for this regarding the second issue is to have the amount of time that each set of motors takes to do a part of its rotation very short. So how this works is basically these stepper motors have 20,000 steps per rotation, and I reduce the amount of steps they take per their turn to 100. This was based on trial and error, trying different things. And so what happens right now is one set of motors for one axis rotates for 100 steps, and then it switches to the other set of motors. They switch back and forth really quickly that to the naked eye, it seems to run very smoothly and running perfectly simultaneous. And this is the reason why it's limited to a maximum strain rate of 11 millimeters per minute. We can try adjusting the number of steps taken by each set of motors per their turn to achieve a higher strain rate at the cost of making them run in less simultaneous fashion, or to make them run more simultaneously but reducing the maximum strain rate that's able to achieve. However, regarding the first issue, which is that the 2 axes can have different strain rates, I wasn't able to find a workaround for this. So here's a video of the stepper motors running. These are the stepper motors for one axis, and they run in the same, they rotate in the same direction as you can see in the video here. They're connected to the stepper driver and the Arduino. The next two programs revolve around the load cell. The first one is a calibration program that finds a calibration factor to convert the load cell output to units of weight. So how this works is I placed masses of known weight onto the load cell and changed the calibration factor until the reading was matching what those weights were. And I used 1 pound weights, 5 pound weights, and 10 pound weights, and adjusted the calibration factor until the reading matched those weights. And one thing I would like to note is that these can be any units. It can be kilogram, grams, whatever. You just have to adjust the calibration factor. The other program is used for reading the output of the load cell, and it requires the calibration factor from the first program. What this program does is it first tars the load cell, so there shouldn't be any initial loading on the load cell, and then it starts displaying the load cell output to the serial monitor. Okay, so future work. What's left to be done is mostly related to machining and assembling the testing apparatus itself, putting the whole thing together, and testing to make sure everything works smoothly. Also, due to the limitations of the Arduino platform, I wasn't able to have the load cell program and the stepper motor programs all together. They work independently, but to have them run simultaneously is currently not possible. So my suggestion is to use two sets of Arduinos, one for running the stepper motors and the other one for reading the load cell output. Or alternatively, if more capabilities are required, then moving to a more capable platform is also an option. After testing the biaxial testing machine and making sure everything works, all the parts are assembled properly and there's no issues, at Frames there's plans for testing a fuselage panel with a window cutout. As you can see here, there's a diagram of what the window cutout will look like. Here you can see the different fiber paths making up the panel that will be tested. Finally, using the test results, an optimum design will be made using 3D printers at Frames. And that brings me to the end of my presentation. Thank you so much for your time and consideration. I'm looking forward to answering your questions soon.